Today we're going to take a look at section 3.1, which is called Numeration Systems. To start with, I would like to tell you a little bit about our numeration system. So the numeration system that we use is called the Hindu-Arabic numeration system. It was developed by the Hindus and transported to Europe by the Arabic. Every now and then, with all political humdrum, somebody will say something funny about writing an answer in Hindu-Arabic, and somebody will freak out. You're like, oh, that's exactly our system. You just didn't know that's what it was called. Yeah. So this is our system. So what are some features about our system, things that you don't even probably think about? All of our numerals are constructed from 10 digits. What is the smallest digit? 0. So 0 up to what? 9. Digits are single values, so 9. So we have 10 digits, but there's not a digit 10. The number 10 is a 2-digit number. Okay, so digit is singles. The place value, we have a place value system based on powers of 10. Right? We have the tens place, the hundreds place because it's 10 squared, the thousands place because it's 10 cubed. It's all powers of 10. Not only that, even the ones place is a power of 10. It's 10 to the 0. So all of our place values are based on powers of 10. And a reminder, we've seen this again before too, but when we have a to the n, it means a multiplied by itself n times. All right, so today, aside from what I just told you right now, is going to be a little bit of history. So we are going to learn about some of the other numeration systems that came before ours, some pros of those systems, and some cons as to the systems and why we don't use them today. The first numeration system that we're going to talk about are the Egyptians. So there's a lot of symbols to draw in, so I'll let you do those first. The first Egyptian numeral is called a vertical staff, and it looks like just a tally mark. The second one's called a heel bone, and it kind of looks like our intersection symbol that we saw back in the last chapter. This scroll looks a little bit like kind of like an incomplete number 9. Lotus flower is a fun one to draw. Looks a little like flower. The pointing finger, I'm terrible at drawing those. It should be so simple and straightforward, and they always look funky. A pollywog, or sometimes it's called a burbo fish, depending on the resources I've used. It's supposed to look a little bit like a tadpole, okay, or whale, something like that. And the last one is called an astonished man. The books that I have used at different points draw these in different ways. So if you're looking at some other resource and you're like, Dr. Hans told me it looks like that. The other book, Aspen took a class for me online, and the symbols don't look like this, at least not all of them. The astonished man in that book, for example, looks like this. I kind of like it better, actually. That's what it looks like. That's what I remember anyway. And so there's some different versions of these and different resources. So let me tell you how much each of them are worth, what's their value. So a vertical staff is worth 1. A heel bone is worth 10. A scroll is worth 100. So what do you suppose the lotus flower is worth? 1,000. The pointing finger? 10,000. The pollywog? 100,000. And the astonished man? 1 million. And I think that he's just excited that he's worth $1 million. That's what I think. All right, so one of the really nice things about the Egyptian systems is it's really easy to read and to translate it back into our system. If you see 2 heel bones, that's 2 tens, so it's worth 20. Okay? So we're going to take a couple of moments to take a look at an example. And the question it's asking is actually something a little different. It takes an example in their system, and it wants us to find the number that comes before it and the number that becomes after it. Okay? So it feels very normal and natural to you at the point where you are in your education for me to say, what comes after 7? And you can immediately say 8, right? You don't have to go 1, 2, 3, 4, 5, 6, 7, 8. Oh, the answer is 8. My 5-year-old, she can't do that yet. We were asking her the other day, what comes after 5? We were trying to count money. She couldn't do it. She had to count all the way up to 5, and then in sequence she could say 6. Okay? So this is not a simple task. It is a developmental task that kids get to. So on this one, if you were to take 3 scrolls and then the heel bone, what I want you to recognize is the bigger values come first, the smaller values come second. Right? So they come in decreasing order. So the smallest value at the end is the heel bone. And how much is the heel bone worth? It's worth 10. So if I'm going to go 1 less than that, what do I actually need? I need 1s, which are the symbol that looks like they call it a vertical staff. It looks like a tally mark, right? So the 3 symbols at the beginning don't change. Still scrolls. But the heel bone, which was previously worth 10, it's not previously worth, it's worth 10, needs to go down 1 and become how many staffs? 9. And no, you can't mark off 5 of them like tallies. No, they didn't do that. There's 9 staffs. So that's the number that comes before the 3 scrolls with the heel bone. What would come after? What would you do to get the number that comes after this?
Just add a vertical line and that number.
You got it. We have our 3 scrolls, we have our heel bone, and we simply attach or add on a vertical staff. Very good. And I'm asking the questions in this order on purpose. The goal is not figure out what this number is, figure out what would come before and after, and then write down their numerical value in that system. The goal is to be able to pause for a moment and put your hat on that says, I'm an Egyptian. Maybe you're not going to walk like an Egyptian, but you're going to think like one for just a moment and think about what would come in before and after within their system. And you might be thinking, why? And the reality is because you're trying to put yourself in a little bit of an uncomfortable position to be able to relate to your kids. Because my 5-year-old can't do this, right? And it's really hard for everyone in here to think, well, why can't she? It's just the number that comes after 5 because you're so comfortable and used to it by now. But you're not comfortable and you're not used to heel bones and scrolls and vertical staffs. Make sense? Okay, but part C on this problem does say, let's figure out what this numeral is in our system. So I have some scrolls. How much is a scroll worth? 100. So if I have 3 scrolls, I would have 300s. And then how much is a heel bone worth? It's worth 10, and I have 1 of those. So what is the numeral value of our 3 scrolls and a heel bone? It's 310. Make sense? Okay, we're going to go the other direction now. I'm going to give you a chance to give it a try without saying much more. You have the number 23,145. And I would like for you to write that in Egyptian. And after you write it with in Egyptian, find somebody nearby and see how your answers compare. Sorry, it's switching back and forth on your pages. You'll be okay. All right, so I can tell that some of you are maybe not the best artists in the room because of the giggling of your classmates. Neither am I, so we'll see how it goes. Somebody tell me, what did you start with the 2 with? What did you draw? 2 pointing fingers. That's how I do mine. Let's see, what do we have next? 3. What's the 3? The 3 lotus flowers.
Is this really what they're called? Like lotus flower?
That's what our book says they're called, so I'm going to go with it. What's the number 1? 1 scroll. How about the number 4? Yep, 4 heel bones. And the last one is a 5. I got the staff thing down. How about you? 5 staffs. Cool. All right, so this is what it looks like. So can you give me sort of a, when would this not be super fun to write out?
When it's huge number.
When it's what?
When it's a huge number.
Huge number. Can you be more specific? Because like if I wrote out the number 1 million, it would be easy.
Well, if it was like a billion.
Okay, say that really loud, Michaela.
99999.
Yeah, like 1 million would be easy to write as a big number, but the number 999,999, yeah, I don't want to do that, right? So a little bit cumbersome for writing out certain types of numbers, definitely. But it's pretty straightforward in terms of conversions back into our system, mostly because of that base 10 part of it, right? Every value is inside of a base 10 place value, right? It's not a place value system, but everything has value that's one of the bases of 10, and that makes it very friendly. So we're about to encounter a system that doesn't have that, okay? So let's take a look at that one. The Babylonians. The Babylonians only have 2 places, or 2 numerals, is what I meant to say. The first one, it looks like a triangle. In fact, probably some of you were thinking upside down triangle, because in our mind we sort of have this image that triangles look flipped upside down from that. That's a value 1. And the other one sort of looks like an arrow that points left, and that one is a value 10. So, hopefully you're sitting here thinking, okay, but that's not very many, and those don't get very big. So what do I do when I don't have, like, how do I write the number 900? Clearly I don't write 90 tens, like something else has to be going on here, and it is. Before we get to that, just in terms of writing these numerals down, I will tell you that I tend to write mine hollow, just for shorthand, and I tend to write my arrow looking like that. So when you see my numerals written out, they'll look more like that. If I've got them typed in from a computer, they're going to look like you see on example 3, but I'm okay with you kind of shortcutting it a little bit on that one. So a couple of properties. This one does have an actual place value system. So what does that mean to have a place value system? Well, if you think about our system, when I have this number right here, that 6 right there is not a 6. What is it representing? 6 tens. So the number 63, right? That's what it means to be a place value system. It means that our numerals are in a place where they're actually being multiplied by whatever the place value is. Okay, so this system, the Babylonians have that. They have place value. But it's not base 10, it's base 60. So what does that mean? Well, again, in our system, I'll do just 3 digits. We have the ones place, the tens place, and the tens squareds or hundreds place, right? And we would keep going up from there. So what do we do in their system? Again, I'll only write 3 of them down. They have the ones place, the 60s place, and the 60 squareds place, and then they would continue on from there if they want, 60 cubed, 60 to the 4th, all that. Okay. One other feature, it's not really written on here, but just as sort of a note, is that larger symbols, this happened in the Egyptians as well, larger symbols come before smaller. So, for example, if we wanted the number 12, we need 1 10, and we would need 2 ones, and the 10 would come before the ones. Is that okay? So larger symbols come before smaller ones. All right, so let's take a look at an example now and see how this would work. Questions are very much like the questions were with the Egyptian system. What comes before, what comes after. The first thing that you have to know and understand is how do I break apart place values? I didn't have to worry about that with Egyptians. They didn't have a place value system, but this one does. How do I decide what's the ones place and what's the tens or the 60s place and what's the 60 squareds place? How do I decide that? Your book will sometimes put a space between them. So you'll actually visibly see some space in there. And so if there's a space in there, you can use that as a demarcation of a place value change. That's fine. The other way that you can use a demarcation of a place value change is because I told you that larger values have to come before smaller ones. So right here, these values are tens, right? And they're coming before the ones. So these can all be in one place value because the tens come before the ones. So all of this is the ones place. I know there's a lot going on in that ones place. But this one right here has to be in a different place value. Has to. Because it's smaller. It's a number 1. It comes in front of tens. And the only way that can happen is if it's in the 60s place value. So this is the 60s place. So imagine you had a system for a moment where you had $60 bills, $10 bills, $1 bills, or something like this. This is saying I have one $60 bill, I have 5 $10 bills, and then I have however many at the end $1 bills. Can you kind of picture that a little bit as to what's going on? That's what's happening. The number at the beginning is in the 60s place. All these other things are in the ones place, but I have two different kinds of values. I have tens and I have ones all in the ones place. So again, when I was talking about the Babylonians, the Egyptians, I talked about the fact that if you're going to go with a number before or after, it would have to affect the end of the number, just like our system, right? 65, I don't change the 6 in 65 if I go up or down 1, right? I change the 5. It always affects the ones place, the number that's on the far right. So if I were to look at this number, and I wanted to find the number that comes before it, what would I need to do? Yep. You'd get rid of, one of these. They're worth 1. Just take it away. Make sense? The number comes before would have 1 fewer of those in it because they're worth 1. So what would it look like? Well, it wouldn't affect the beginning of the number. So I'm going to have the triangle, and then I'm going to have the 5 arrows. And then how many of them are there in the number I gave you originally? 9. So if we remove them, there will now be 8. Okay, 1 less. There's 1 less triangle. Everybody good? What happens if you add 1? What's the next number after this? Well, I'd have to add 1 to the triangles, right? And so I had 9, which now makes 10. But I have another symbol for a 10. It's an arrow, which now gives me 6 arrows for the value 60. That's where you're getting at, right, Colton? Yeah. So I would need 60 over here and where I've got the red. And I already have a 60 in front that's kind of marked off in pink, right? There'd be one of those too. So within the place value, what happens after we leave the number 9 and we want to go up 1 in our place system? What comes after 9? 1 and a 0, right? It becomes a 2-digit number. And if I have a 3-digit number and I exceed the value, I have to have a 4-digit number, right? Same thing. So same thing here. I now have 60 in the ones place, but this is a base 60 system. I can't have 60 in the ones place. Just like in our system, I can't have a 10 in the ones place or a 10 in the tens place. I need a single digit number, right, in our system. Same thing here. So what do? Well, I would have the original 1 that I had before at the very beginning. That didn't change. But then that 60 that's in the ones place now has to become a 1 in the 60s place, so I need another one. And we run into a problem. What's the problem I run into?
It could be 2 or it could be 2.
Yeah, this is supposed to be representing the number 120, 60 and 60, but this is exactly how you would write the number 2. And that's a problem. How else could the value in B be interpreted? As 2. Or perhaps you could interpret it as 61, actually, if you believed that it was 1 and 1 like this. A 1 in the ones place and a 1 in the 60s place. I did that backwards. 1 in the ones place and 1 in the 60s place, right? But we wanted it to be worth 120. 120 is what we were hoping for. Unfortunately, in this system, there is no placeholder, right? In our system, we don't have this problem, right? We just put plunk a 0 in there. There's 0 in the ones place, no problem. They don't have a 0. They don't have a placeholder at all. And aside from this ability to sort of like give a little bit of space in between them, they don't have like commas to separate things either, right? There's none of that going on. So if I wanted to write the number 61, it would look like this. It looks just like the 2, especially if I'm not being careful or I write sloppy, right? How do I know for sure there's a space there and I'm not just assuming that you've put a space there? Those kinds of issues. This is a problem. So what is the value that we originally had in our system? Well, the original number that we were given had a 1 here, it had 5s here, or 5 arrows here, and then it had 9 of these. We talked about the fact that we have to draw a place value break here because it's smaller number in front of larger number. So in the original number we were given, this is the 60s place and this is the ones place, right? There is a 1 in the 60s place. And what is the value in the ones place? 59. So what was the original number we started with? $119, right? Is that what we had? 119. This system's pretty complicated for many different reasons. Number one, it's complicated because it's in base 60 and we're not comfortable with that. We're comfortable in our base 10 world. We're not real comfortable in base 60s. It's also not comfortable because I don't have place value holders. Like, what if I needed, sort of imagine if I had the ones place and the 60s place and I have the 60 squareds place and what I really wanted was a triangle here and a triangle here. What am I supposed to do about that? There's just not a good way to differentiate some numbers from each other, right? Because they don't have a place value holder, stuff like that. So there's just some real sort of oddities that occur because of some lack of structure that we have in our system. So we're going to take a number now that's in our system and write it in their system. We've already seen this number once before, 43,205, or at least I think we did. No. 245. Oh, ours was different before. That's right. I think I used this one later. Okay, 43,205. And we're going to write it in Babylonian. So here's the deal. We already said just a moment ago that Babylonians have these powers of 60. So this is the ones place. This is the 60s place. This is 60 squared. And we'd have 60 cubed. And what I need to know first is I need to know what those values are sort of in their simplified form, not in factored form, okay, not as squares. So what is 60 squared? 3,600. And what is 60 cubed?
260.
216,000. And I contend that 216,000 is too big. Why?
It's over the 43.
Yeah, it's more than my 43 I'm starting with, so I don't need this place value. What I have when I'm done, or what I will have when I'm done, will be a 3 place value number. Okay? So how do I figure out what numbers go in each of those places? Well, I'd like to show you sort of a process that we're going to continue to use throughout this section, and it's a division algorithm process. Algorithm just means way of doing things. And I would like for us to take that number 3,600 and write this down sort of like a top hat. And the number that we are dividing the 360 into is the 43,205, and it goes underneath the hat symbol like that. Grab your calculator. You're definitely going to want it today. Okay, if you don't have one with you, just wait and watch what we got going on. But what I want you to do is I want you to divide. How many whole number times will 3,600, I'm left off from a 0. How many whole number times will 3,600 go into 43,205? 12 times. And then we're going to use our calculator and we're going to say, well, what is 3,600 times 12?
43,200.
43,200. And we're going to subtract. So what is 43,205 minus 43,200? 5. Now, we're going to see the why on this later, but for now, what I want to tell you is you will always divide by the next place value. The next place value is 60. How many times will 60 go into 5? You're answering how many times 5 will go into 60. My question is, how many times will 60 go into 5? What did you say, Colton? You all said 0. Okay, I heard 12s in other places. It's 0. 60 doesn't go into 5, right? So this is the easiest multiplication of the day, 0 times 60. I still have my 5, and then I will divide by my 1, because it's the last place value. Obviously, 1 goes into 5 times, leaving with a remainder of 0. We always get down to a remainder of 0. You are not done until you are at remainder 0 and you have divided by all the powers, which means you always end up dividing by 1 at the end. Okay, so we still haven't actually done the process of the answer. How do I write a 12 in Babylonian? Arrow and 2 triangles. Now what I'd really like is I'd really like some symbol for 0, but I don't have one. So I can't write anything down. At the best I could leave sort of a placeholder like space, but there's nothing to write there. The next digit says 5, so how do I write a 5? Yeah, sorry, I wrote that wrong. 5 triangles. So this is my absolute best case scenario way to write this. And it's still not good. Because even so, with that space there, I may have separated sort of these from these, right? I did separate those, but there's still no way to indicate that there's like this missing something in here that's a number and it's a 0. So at best scenario, we might think that this is 5 1s and 12 60s when it's really supposed to be 12 60 squareds. Does everybody see the problem here? It's a legit problem, not good, but it's the best that we can do. All right, so this is in fact our answer. So those are our friends, the Babylonians. You ready to meet our next folks? Our next folks are the Mayans. The Mayans have 3 symbols: a dot, a line, and it's a shell.
Or what it's called.
Yeah.
I know
So-
online it looked like a football.
Yep, it looks more like a football in the other book. Yes, it does. The dot's worth 1. The line's worth 5. The shell's worth 0. And hallelujah, we got a 0! Because that was the biggest problem in the last system. There were other problems too, but that was a big problem, not having a 0. So a few other features about the Mayans. They have a place value system as well. Theirs is a modified base 20 system. So what does that mean? Well, it means that they have, let me actually go to the next one. It's actually also written vertically. And then we put dots on top of bars. That's how they do it. So bars go underneath dots. So they have, if we're thinking vertically, this first one would be the ones place. Those are not bars that indicate the number 5. They're just placeholders, okay? And then they would have the 20s place. That's what would look like if we're base 20. The next one would be 20 squared, 20 cubed, and so on, but theirs isn't. The next one is 20 times 18. I know. And then 20 squared times 18. And then 20 cubed times 18, and so forth. So that's why it's called a modified base 20 system, because we get this random 18 thrown in there, or at least it seems that way. So just for the moment, let's actually write down what each of these place values are worth. The first place is obviously worth 1, and then 20. What's 20 times 18? 360, and then if we multiply that by 20, we get 7,200, and what's our next one? 144,000, and it would keep going up from there, but yeah, so let's chat for a moment about this line right here. Whoops. I wanted to do this. What's going on in this spot? 360. These are the Mayans. Any idea why 360 would be special? The Mayans were very into their calendar that was supposed to end the world in 2012. And we're still here. So you're exactly right, Hannah. It is about their calendar. So what is 360 so special? What is it approximately? Okay, it is a circle, but that's not related to the calendar. So degrees in a circle is what you're thinking of. It's approximately the number of days in the year, right? It's close. It's really close. These are ancient people. This is a really good estimate, right? 360 when it's supposed to be 364 and roughly a quarter. It's a pretty good estimate, and that's why this is happening. Why do you suppose it's a base 20 system to begin with? I mean, we use base 10. Do you know why we use base 10 and they use base 20? Nope, it's not. It's a good guess. Let's talk about us then first. Why do you think we use base 10? Why do we use base 10? Because we have 10 fingers. And no, the Mayans did not have 20 fingers. We have 10 fingers. That's why we use base 10. Like literally, if God made us with 8 fingers, we would be working in base 8 right now. And we would all be just fine with it. And we wouldn't think anything about it as being weird. We use base 10 because we have 10 fingers. So why do you think the Mayans might have used base 20? Because they have, just like us, fingers and toes. But yeah, right? I mean, like, I don't see any sandals today. Is anybody wearing sandals today? If you were Mayan, you would have been, right? Or barefoot, right? It would have been normal and natural to have all 12 or all 20 of your appendages showing all the time, right? Like that would have been normal. That's where that's coming from. All right, so let's take a look real quick before we leave class today of one example of the Mayans. The Mayans, dots above lines. So how do we know where a place value switches? Well, it switches when a line comes above a dot, because they're not supposed to, unless it's in a different place system. So this is a 2-digit or 2 place value number. I have 2 dots in a line. How much is this one worth right here in this spot? Just for reference. Sorry.
40 because there's 2 20s.
Nope. I'm not asking for the place value part of it. How much is this worth? 7. Line's worth 5. 2 dots. 7. You good? Yeah, okay. How about the line with the 4 dots underneath? That's worth 9. Okay, so we're not changing the number right now, but recognize we've got the lower place value. So anytime we're talking about adding or subtracting 1, what number comes before, what number comes after, it always affects the lowest place value, and the lowest place value is the bottom of their number. Just like on ours, it's the far right-hand side of our number, the lowest place value. It's their bottom of their number. So whatever is happening, I'm affecting the 9 at the bottom. Make sense? So if I need the number that comes before this, what would it look like? Yeah, I just take away a dot. So 2 dots in a line, top number doesn't change. It's the larger digit. It doesn't change. The bottom one would change to having only 3 dots. I just take away a dot from the bottom. What about the number that comes after? Yeah, I'd add a dot. And what would, Michaela, you're about to tell me what happens when I add a dot here. Yeah, I'd have 5 dots, and 5 dots is equal to a line. So now, I have 2 dots and a line that were already there, and now I have 2 more lines. That's not confusing or anything, right? Now I don't have that super convenient way to say, oh, look, dots and lines, they switched place value like it did at the beginning. I don't have that. This one actually looks a lot like another digit. What did it look like? It should look a lot like 17, right? Each line's worth 5, 2 dots, 3 lines and 2 dots, so it could be 17. 2 dots, 3 lines. I mean, there's not a good way to do that and to know for sure that it switched. Even if there's a little bit of space there, you have to analyze, is it enough space to justify that I've switched place values? It's hard to see. So yeah, I gained a 0. That's good, but the 0 didn't fix this particular problem. So what in the world is this number then? Well, the original number I started with, that is. Well, I had a 7 and a 9, right? And at the beginning, Colton was trying to tell me that that 7 is in the 20s place, and he was exactly right. And then the 9 is in the 1s place. Yeah? So what is this number? It's 149. The original number I began with is the number 149. Okay, we have one more example in Mayan to take a look at, and we will look at that next time. And I would like for you, if you have a chance and you're near enough you can see it well, to take a really good look at the clock on top of Rayleigh Chapel. And we're going to talk briefly about the clock next time. It has Roman numerals on there, and we're going to talk about the Roman numerals, okay? But if you have a chance, just take a really good look at it, maybe even snap a picture and think about it, and we'll chat a little bit about why next time.